Hello and welcome. In this video, we're going to learn how to expand binomials using a more efficient method. So when I say expand polynomials, I mean like the quantity x plus 5 to the 7th power. Instead of having to multiply each of those terms by hand, actually using this shortcut, this trick called Pascal's triangle to help us expand in a more efficient way. So let's go ahead and jump right in. Okay, so we're going to consider expanding expressions of this form. So we have a binomial to the power of some whole value, whole number, n. And what we're first going to do is we're going to look at the pattern that we notice when this happens. So if n is 0, then we just get a plus b to the power of 0. Anything to the power of 0 is 1. If it's to the first power, then we get a plus b to the first power, which is just going to be 1a plus 1b. If we do it to the second power, we learned the property there back in Algebra 1 and reviewed it in the last video, we end up with 1a squared plus 2ab plus 1b squared. If we do it to the third power, which we also looked at in the last video, we end up with 1a cubed plus 3a squared b plus 3ab squared plus b to the third. If we were to keep going and to continue expanding to the fourth power, it would look like this. 1 times a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. So Pascal, who was a French mathematician, it was exploring this relationship to try and develop a more efficient way for us to multiply as opposed to actually having to write a plus b times a plus b plus a times a plus b 4 times or 5 times or 6 times. What he wanted to do was observe the behavior that he saw and see if there was some sort of pattern. And there's a lot of different things to notice about this expansion. The first thing to notice is that the outside terms, the very first term and the very last term, anytime you expand, is really just whatever this first term in our binomial is to that highest power. So a to the fourth. And the last term is always going to be that second term to that highest exponent, b to the fourth. The terms in between are combinations of what happens when we multiply a times b and a squared times b squared, but there's a couple things that I really want you to notice. If we look at this whole red polynomial in terms of a, we start with our a to the fourth power, then we get our a to the third power, then we get our a squared, then we get our a, and then we get our term that doesn't have an a. So it's in standard form in terms of a. Each term, the exponent with a, is decreasing by 1. And at the same time, each time the exponent with b is increasing by 1. So technically, we could have b to the power of 0 here. That would be 1. So we would end up with the same thing. Then we have b to the first, b to the second, b to the third, b to the fourth. So this pattern that we're going to use, we're going to first look at how the triangle is formed. And then we're going to talk about how we can use the numbers in Pascal's triangle to help us effectively expand polynomials without having to just continue to multiply binomial upon binomial upon binomial. So here's how the rows of Pascal's triangle are formed. First thing to notice is that all the numbers on the outsides are 1. So anytime you start a new row, you're always going to start with 1. And again, we can observe that behavior happening here. So the outside rows on both sides are always 1. We always start and end a row with 1. From our observed rows, we know that anything to the power of 0 is 1. And then the second row, we had our a and our b, both to the first power. And then the third row, we had 1a squared plus 2ab plus 1b squared. So what we're really looking at here, these numbers are the coefficients that we identified off to the left. So in our third row, we see that we have 1a cubed plus 3a squared b plus 3ab squared plus 1. What I want you to also notice is that the way that we could get these numbers is simply by adding the two numbers right above it. And that's not a coincidence. That is a part of what is happening when we're expanding those polynomials. So 1 plus 1 is 2. 2 plus 1 is 3. 2 plus 1 is 3. And this keeps going. We always bookend with 1s, but the next number in row 4 is what I get when I add 1 and 3. And when I add 3 and 3, and when I add 1 and 3, and then we end with a 1. So similarly, 1 plus 4 is 5, 4 plus 6 is 10, 4 plus 6 is 10, 4 plus 1 is 5, and we bookend with our 1s. So now that we've talked a little bit about where Pascal's triangle comes from, let's make sure we actually understand how to sort of create it and add numbers in as we go. So let's actually just take these first 5 terms, and then let's keep expanding and get all the way to having 10 rows of Pascal's triangle. Okay, here we go. So let's look at the next row. We know we're going to start with a 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And we bookend with a 1. So there's our 6th row. Our 7th row, again, that'll be the one that has a 7 in it, will be 1. 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. 35. 21. 7, and we always end with a 1. Our next row is going to be our 8th row. 1, 8. 21 plus 7 is 28. 21 plus 35 is 56. 35 plus 35 is 70. 35 plus 21 is 56. 28, 8, and we bookend with 1. All right, I want you to pause the video and try and fill in the last 2 rows on your own, and then unpause the video to see how you did. And there we have it, completed to 10 rows. So most of the time, realistically, we're probably not going to be finding something to the 10th power, but we are now capable of doing that using Pascal's triangle. So let's actually talk about why this is going to be helpful, and then talk about how we in fact use Pascal's triangle to expand, how we can use the numbers in this triangle to make our lives easier. But let's start with why in the world you would want to create pieces of this triangle to help us. So let's look at an example. Okay, here we have x minus 2 to the 5th power. And if we haven't learned, which we really haven't yet, how to use Pascal's triangle to help us, all we know so far is that this is x minus 2 times x minus 2 times x minus 2, and we're going to have this 5 times. And this already kind of seems like a lot, and maybe you don't think it is, but the first thing that I guess I would do is I would say, well, I know that if I multiply 2 of these, I'm going to get here. So if I multiply these 2, I'm also going to get here. Then I still have another x minus 2. So now I have to multiply in some order these 2 trinomials by this binomial, and I need to simplify this as much as possible. And again, the algebra is not going to be crazy here, but there are a lot of places where we can mess up. So I'm actually going to encourage you, pause the video, work through either the way that I started or your own way, multiplying these polynomials without using Pascal's triangle, which is going to be our shortcut here. Then unpause the video and see how you did. So here's my next step. Now I'm going to combine like terms in blue before I multiply the purple. And now I'm going to distribute this 5-term polynomial to my x minus 2. And now I'm going to go ahead and combine like terms here to get my final simplified expression. Now that was a lot of work and a lot of places that we could go wrong. So the goal that Pascal was trying to help with was, how do I do this more efficiently? How do I do this without having to keep multiplying, putting myself at risk for making little mistakes along the way? So let's talk about how we're going to use Pascal's triangle to help us expand a binomial. And I'm actually going to leave this answer on the screen and just move it up so that we can practice on this exact same problem and check that our answer was right. Okay, so if we're going to use Pascal's triangle, the very first thing that we need to do is we need to determine the row that we're looking for, or that we need to use. In this case, since we're looking at something to the 5th power, we need the numbers that go with row 5. So we just talked about how we could form this, but since we already came up with this, I'm going to just identify that that row is 1, 5, 10, 10, 5, 1. So the very first thing that we're going to do is identify the row that we need. If it was to the 4th power, we'd need row 4. If it was to the 10th power, we would need row 10. So what we're going to do now is we're going to take each of these coefficients and rewrite them. So I'm going to write 1, I'm going to leave some space and write plus 5. I'm going to leave some space and write plus 10, another plus 10, another plus 5, and a plus 1. And I might need to give myself a little bit more space. We'll see as we go. So step 1, identify the row that you need and write out your coefficients. Leave some space. Then we're going to take each piece, just like Pascal thought about it as part A and part B inside. We're going to take each piece. So I'm going to take the first term of the binomial and rewrite it with each of those coefficients. So I'm going to say starting with the highest degree. And I'm going to make a little note to you, use parentheses. So what I mean is I'm going to have x to the 5th, and then I'm going to descend. I'm going to go down x to the 4th, x to the 3rd, x squared, x to the 1st, x to the power of 0. Now, x to the power of 0 is just going to be 1, but I want you to see each time we're using each term. Our ultimate goal is to get back what we have up here. Now I'm going to do the exact same thing. So repeat step 2 with the second term. And the reason I want to make sure that I always have parentheses, so now now I'm going to start with 0 and I'm going to go up. -2 to the 0, -2 to the 1st, -2 to the 2nd, -2 to the 3rd, -2 to the 4th, -2 to the 5th. The reason I want to make sure that I have parentheses is because I want to make sure everything that's a part of that term is being put to whatever power we're looking at. And then last but not least, now we just need to simplify. So we have all the terms that we need here to simplify to get us back here. So 1 times x to the 5th times -2 to the 0. Well, -2, anything to the power of 0 is 0. So this whole first term is just x to the 5th, which is what we're supposed to get. Our second term, 5 times x to the 4th times -2 to the 1st. Well, 5 times -2 is -10, and then we have x to the 4th. Now we have our second term. Now we're going to look at our third term. I know my third term is going to have x to the 3rd. -2 squared is 4, so I'm going to have 10 times 4. So this is going to give me plus 40x to the 3rd. And I'm going to look at the next term, which I know is my x squared term. -2 to the 3rd is -8, and 10 times -8 is -80, so -80x squared. And then here I have 5 times -2 to the 4th, which is 16, times x, and that's going to give me 80 as well, so plus 80x. And my last term, x to the power of 0 is 1, so I just have -2 to the 5th, which is -32. And look at that. We have the exact same answer without having to do all of those steps expanding. So what I want to do, this is all we're covering in this video, is I really want to just work through a few more examples so that you can get a feel for how this works. Okay. So let's do 2 together, and then I'm going to have you try at least 1 on your own. Step 1, figure out what the row is. So if I didn't know, I could just start redrawing here, but this is the row that I need. I know this is the row that I need because that's the exponent that I need, and this is the row that will be to the 3rd power. So I'm going to rewrite those coefficients. 1, 3, 3, 1. Then I'm going to look at my first term. That whole term is going to go to that highest power. Then that term to the second highest power. So we're decreasing that exponent by 1 until we get to 0. With our second term, we're doing the opposite. We're starting at 0 and we're increasing it until we get to 3. Now we're going to multiply. Now, one thing I want to remind you is that 3y to the third power that this is 3y times 3y times 3y. So everything inside gets this exponent. So 3 to the third power is 27. So this is 1 times 27. 1 to the power of 0 is just 1. So this is 27y to the third. Here, this is 3 times 9y squared times 1. That's going to be plus 27y squared. Here, this is 3 times 3y times 1, which is going to be plus 9y. And here, 3y to the power of 0 is 1, and 1 to the third is still just 1. So here is our expanded expression. Isn't that so much more efficient than actually multiplying each piece out? Okay, let's look at another one. All right, here we go. Step 1, figure out what the row is. This is the 4th row. So I need the row that has a 4 in it. Here's the row I need, so here are my coefficients. So 1 plus 4 plus 6 plus 4 plus 1. First term is z, so z to the 4th, z to the 3rd, z to the 2nd, z to the 1st, z to the 0. And then this is a plus 3. So 3 to the 0, 3 to the 1, 3 squared, 3 cubed, 3 to the 4th. And now simplify. 3 to the power of 0 is 1, so I just have z to the 4th here. Here I'm going to have 4 times 3, so 12z to the 3rd. Here I'm going to have 6 times 9 times z squared. Well, that's going to be 54 z squared. Here I'm going to have 4 times 27. I'm going to do that off to the side over here. That's going to give me 108 z plus 3 to the 4th, which is 81. So hopefully it's starting to feel more comfortable. We're going to work through 3 more examples, but I'm going to put the next one up, and I'm actually going to encourage you to set it up on your own. Okay. So I don't want you to do everything on your own. I just want you to figure out what that row is and see how far you can get in the setup process on your own, and then unpause the video and see how you did. Now, I probably should have given myself a little bit more space here, but go ahead and check that you have the same first step, then pause the video and simplify through, and then unpause the video and see if you got the same final answer. Again, it's really important that you remember that that exponent applies to both the 2 and the t. So 2 to the 5th is 32, t to the 5th. And that negative 1 to the power of 0 is just 1. This is going to become minus 80 t to the 4th. Minus is coming from this. 5 times 2 to the 4th times negative 1. Plus, negative 1 squared is positive 1, so I have 2 to the 3rd times 10. That's going to give me 80 t cubed minus, because negative 1 to the 3rd is negative, 2 squared times 10, so 40t squared, plus 5 times 2t times positive 1, so 5 times 2, 10t, minus 1, because 1 to the 5th is just going to be 1. All right, I'm going to put 2 more up, and I'm going to have you work through both of those on your own. If you can get through those 2, then I think you have mastered, or at least are on your way to mastering using Pascal's triangle to expand binomials. All right, here you go. Go ahead and set them up and work all the way through them, and then unpause the video to see how you did. All right, pause the video and check over those answers, and then go ahead and write down any questions you have. This whole video was just about Pascal's triangle and using it to expand binomials. I look forward to supporting you on this. Thanks for listening.